sensitivity of the model to some hyperparameters. Okay, when we try to analyze some data, okay, try to solve a problem. Okay, I think neural network is one of the way you model the data. Okay, you have a model and try to construct a relationship between the input value and the output you target. Okay, so you will try to construct a neural network as a designer. Okay, I mean neural network structure designer. You have to decide, okay, what kind of model you would like to use. I mean, how many layers you would like to use, and in each layer, what kind of layer. For example, it's a dense layer, or it is a convolution layer, or it is a max Pooling layer you would like to use. And in each layer, there are several hyperparameters, which means how many neurons you would like to use, what kind of optimizer you would like to use, what is the learning rate you want to apply in your optimizer. So there are several different parameters you may choose. Okay, as a designer, you have to choose what kind of parameters, what's the value you want to use, because those values deeply influence the effectiveness and the efficiency of your model. So here's a list of hyperparameters. For example, learning rate schedule, loss function. Okay, the right hand side is the sensitivity, which means if you try to fine-tune those hyperparameters and how sensitive those hyperparameter is, if you change this value with high sensitivity, that means your model changes a lot. So you can more quickly, I use the word quickly, okay, you can more quickly to tune your model to fit your data. However, as we mentioned before, sometimes we have some problem called overfitting or underfitting. That means you don't have to tweak your model so quickly, because sometimes your model is too aggressive. If your model is too aggressively to do fine-tune work, the model will remember, I use the word, okay, remember, the model will remember the data you use and try to memorize what is its output. Okay, I will draw a figure afterward. Okay, that is not a good situation you would like to encounter, because your model would prefer remember the answer, not to really build the relationship between X and Y, your input and output. So your model, when you do testing or you do validation, okay, your model would be a little bit overfitted. So here is a list. Okay, so if you have a model, okay, no matter what it is, it's a convolution or it's just a very simple dense neural network. If your model does not perform quite well, okay, try to modify those hyperparameters from the top side. Okay, learning rate, you can change the learning rate. For example, the learning rate we mentioned here is the initial learning rate. In our previous lecture, we have explained some different optimizer. Those optimizers will change your learning rate when you do the training. So for example, some add-on optimizer, ADA optimizer, they have some different concept like momentum, like change the learning rate. So the learning rate we write here is the initial learning rate. If your initial learning rate is too large, that means you can explore your loss function surface, but it might not be able to find the lowest loss function value. That's because your learning rate is too large. So every time when you do partial differentiation, okay, you might not you have a right direction, but as we mentioned before, sometimes it's not possible to find the lowest loss function value because the learning rate is too large. That means you every time you change your span, your direction, okay, you can it's not that fine-grained. Okay, so sometimes you need a small learning rate. But usually at the end of your training, if you encounter some situation like every time when you train your neural network and you observe that the loss of the loss value, it seems like it does not decreased very aggressive, you can try to increase your learning rate at the beginning of your training. So as the initial value of training, it might be able to push your loss function value to a much lower point at the beginning of your training. So learning rate is the most sensitive hyperparameter we can try to fine-tune it. And the second one is the learning rate schedule. It is related to the optimizer you use, because sometimes your optimizer, as we mentioned before, your optimizer will use the initial learning rate, but it will change the learning rate. So sometimes you need a very large learning rate at the first beginning of your training, and conceptually you need a small learning rate at the end of your training, so that you can explore your loss function surface at the first place, and at the end of your training you can find the lowest loss function value. Okay, so that is the learning rate schedule. Loss function, again, as we mentioned before, if it is a regression problem, okay, so your target value y, it is a numeric value. Usually we use MSE or square root of MSE. That is good enough. For the classification problem, okay, usually we use cross entropy, or we use sparse cross entropy. You can check them out in the Keras API, so you can most time cross entropy is good enough. But for some application, if you want some very specific loss function, because if you know your y, they need to fit some distribution, they need to you want to improve it rather than use regression, which means you rather than use MSE or cross entropy, you can design your own loss function. At Keras, it has a function that you can customize your loss function. Sometimes when you use cross entropy, or sometimes you use MSE, try to apply regularization as well. Okay, we talked about last week. When you apply regularization, Lasso regularization can help you to do feature selection and to prevent overfitting as well at the same time. Next is units per layer, which means how many neurons you choose to use in each layer. The second one, most of them are related to network structure. Okay, how many layers you want to use, how many neurons you want to use in a layer. As we mentioned before in the last week, I think this is the most important topic we talk about. Those activation function, those neurons, those layers, they are simply just some way to push or twist your original space to another new linear space. How many times you want to fold your original space, and how many times you want to create a boundary line in your original space. So try to modify them if you think the learning rate and loss function is good enough, and you think that the performance of your neural network is not good enough. So you can try to fold your original space. Okay, so that is, and the second one is the parameter initialization strategy. I think we haven't discussed this strategy. As we mentioned before, when we do, for example, regression, use a neural network to do a regression problem, but we don't know this value. If we do MSE, okay, this question we write it a lot of time. That is A and that is B, and we can draw value. So that is a higher place and that is a lower place, right? At the first place, okay, when we do gradient descent, okay, we simply just select a random value of A and B. Here, theta is A and B, T is 0. So we simply just random select an A and B and see how it performs, okay, based on the value of MSE value, okay, that is MSE Bayesian. By partial differentiation, it tells us how where is the direction of A and B. Okay, maybe A says, okay, if you do partial differentiation on X, okay, so it knows, okay, A should go this way and B should go this way, so that we can have a lower MSE value. So basically we go this way. However, that is the first data point we choose, which is theta, T equals to 0. So at the second data point, maybe it's right here, right? So that is theta. Okay, the second theta, the better theta, after we do partial differentiation. Parameter initialization strategy, which means at the first beginning, we said you can simply just randomly choose initial value of your A and B and try to do gradient descent to find the next theta, next. So you will get the optimized theta. So, but sometimes, Okay, choosing the initial value might be important in Keras or in TensorFlow. Sometimes we just simply use the simplest strategy. When we choose different initial parameter of A and B, okay, those weights, usually we use a random strategy, which is okay. But sometimes in Keras or in TensorFlow, okay, they have a specific strategy. So for this weight, okay, it can be a very, like, for example, it's a 300 dimension. So basically, we have to choose a lot of random values as their initial values so that we can do partial differentiation. When we do randomly choose some parameters, TensorFlow or Keras, okay, they simply just have a normal distribution, which is mean value is 0 and their standard deviation is 1.0. Those very nice functions. They help you to randomly select values and use those values as those initial values. So that is one of the strategy you can set those values. So the value you use right here, W0 to W299, their initial values comes from a very simple normal distribution, which is mean is 0 and its standard deviation is 1.0. On the average, half of the weight, half of the initial weights, they are less than 0, which means they are negative numbers. And half of the weights, they are positive numbers. And lots of weights, their initial value are 0 because the mean value of this specific normal distribution is zeros. Okay, but after that, when we do the first partial differentiation, those values will be changed, right? Will toward the direction of lower MSE value, right? For example, I have a proper learning rate and have a proper number of units in each layer, number of layers, and have a very common loss function, something like that. But it seems like my model does not move, which means every time I do partial differentiation, those weights, it seems like they do not move quite obviously. So maybe that is a time you would like to change such kind of strategy, initial weight strategy. Half of your weights are currently negative number, half of the weights are positive number, and some of the weights are zeros. Zeros means, which means some of your axis right here, right? So that means, okay, x1, x2, x0, x299. Some of the weights initially, okay, they do not pass any information from the input to the right hand side, or some of the initial weights, they are quite close to 0, right? Because your weight is randomly choose from a normal distribution. A lot of randomly chosen weights will be close to 0. So maybe that is one of the reasons that initially your information, which is your x0 to x299, does not pass to the right hand side. So that the partial differentiation does not quite did its job. So sometimes you can, you can choose some other way to initialize your strategy. Okay, you can check them out in Keras. Okay, there are several different ways to initialize your weight. So that is the parameter initialization strategy. Okay, they're related to how your neural network looks like at the first beginning. Okay, but as I mentioned, even if you don't choose different strategy of parameter initialization, okay, if your learning rate and if your optimizer is good enough, they will gradually change those weight. Although the speed of changing those weight would be a little bit slower, but eventually they will find the direction of the lowest loss function value. Layer property, that means if you use different kind of layers, such as convolution, such as dense function, max pooling, there are a lot of different layers provided by Keras, but we only mention some basic ones. So different kind of layers, okay, they indeed has different sensitivity. Okay, degree of regularization, which is L1 regularization and L2 regularization. Okay, choose of parameters we also talked about before. The last one, optimize the parameters, size of mini batch, choose of a linearity, the last sensitive ones. The size of mini batch, that means every time when you do partial differentiation, how many data you would like to use in your training data to do each run, each run or each epoch. Okay, if you have, for example, if you have a lot of different data, right? Okay, you can simply choose part of the data. Okay, and you apply those data in your NSE. Assume it is a regression problem. Okay, you can choose part of data when you do training. You calculate the next weight, okay, by using part of data. Okay, that is what we call mini batch. Okay, the next time when you fine tune your weights, next time you can use another part of your data to do next time training, and so on and so forth, so on and so forth. And of course, if we divided our data into 3 different mini batch, and you can do partial differentiation each time by using one of those data set. So of course you can repeatedly use these 3 different mini batch. Okay, for example, you can train your neural network, for example, 300 times. Okay, 300 times, and each time you use different data set. So at the end of your training, okay, we say mini data set. Okay, mini data set, they are trained 100 times because you trained it 300 times in total, and each time you use different mini data set. So each mini set has been trained 100 times. Okay, that is one of the strategy you use. Of course, you could train the data set, for example, 3,000 times. So each mini data set will be trained 1,000 times, but that might not be a good strategy because you train those data set too many times, so it might encounter some overfit situation. So you have to select proper times to do such kind of training. Okay, how many times you want to do the training? For example, okay, you have 300 times training process you have to do. So the first time you use this data set, the second time you use one, and the third time you use one. And at the 4th time you do the training, you can simply just again use the first mini data set. That is okay. But sometimes, okay, if you think you want to make your model more robust, at the 4th time you can sort or random. You can randomly shuffle this data set. And in this shuffle data set, you can again partition this data set into 3 different mini data set. And at the 4th training, you use one of the data set after shuffling. That is one of the way you try to improve your model. Okay, that is one of the way. Okay, you can choose different strategy, and of course you can change the size. For example, you partition your data into 3 different mini set, 4, 5, 6, 7. It all depends on you, and how many times you like to go through all your data set, which is right here, the size of mini batch. How many batch you like to do? 1,000 times, 100 times. The choose of non-linearity, which means the activation function you choose. In the previous class, okay, we talked about activation function, right? Activation function. Different activation function will push or twist your original space to a new linear space, right? So basically they present different non-linear relationship between your layers of your neural network. So basically, I think that is okay. This figure, I think this when you try to fine tune your neural network, okay, try to, if your neural network does not perform good, okay, try to modify your neural network. Okay, I think that would be helpful. Okay.